Hi everyone. Today we're going to talk about Friedel-Crafts acylation of ferrocene and chromatographic separation of the starting material and product. The discovery of ferrocene was really a paradigm-shifting landmark event in chemistry. It revolutionized the field of organometallic chemistry, and numerous related complexes have since been characterized and used for many different purposes. Ferrocene is known as the first sandwich compound, and here you can really see the unusual structure. Ferrocene has an iron that is presumed to be in the 2+ state, and it is bound above and below, as shown, by two cyclopentadiene anion ligands. Now, cyclopentadiene, the pi system there contains in each ring contains 6 electrons, so it's aromatic, and the iron is actually bound to the pi system, the entire pi system above and below. And if you take a look at some other non-benzenoid aromatic compounds, and you see cyclopentadienyl there in the bottom, on the bottom second one from the right. Just as a reminder, of aromaticity apart from a simple benzene. So ferrocene actually undergoes a Friedel-Crafts acylation. You can use the typical Friedel-Crafts conditions, but it turns out ferrocene will also react under the conditions shown with acetic anhydride and different acid catalysts, and this is because ferrocene is actually more reactive than benzene in Friedel-Crafts acylation. The reason people give is that it's the cyclopentadienyl that gets substituted is negatively charged, so it's more nucleophilic. Now the mechanism is interesting. Again, it's really a simple Friedel-Crafts acylation. So the electrophile that you're going to form is going to be the acylium ion. The acylium ion and acetic acid are going to form from the interaction of your acid and the acetic anhydride, and then the acylium ion is going to be attacked by one of the cyclopentadienyl anion rings of the ferrocene. And then, of course, you'll rearomatize by losing a proton via the acetate anion. So once you've done your reaction, you're going to want to separate the leftover starting ferrocene from acetylated ferrocene. And as you recall, we've already studied gas chromatography and done some chromatography before. All chromatographic separations are based on the balance between how strongly compounds to be separated adhere to a stationary phase versus their affinity for the mobile phase. So compounds that favor stationary phases are retained for a longer time, and as a result they move more slowly down a column than do compounds that favor the mobile phase. So let's take another look at what you're going to be using in your column when you actually do the separation is alumina. What you're going to be using in your TLC or in thin layer chromatography is going to be Silicagel, and these are the most commonly used stationary phases or adsorbents, and they're relatively polar, and organic solvents with different polarities, you see a polarity scale there on the right, there are several in your textbook as well, they make up the mobile phase. So the more polar the eluent, the greater is its eluting power. That is, because the stationary phases are polar, if you use a more polar eluting solvent, it's going to compete more readily with the stationary phase, and it's going to move your organic compounds down the stationary phase more quickly. So some differences in TLC, you're actually watching the solvent go upwards. It actually moves upwards, and in the column you're moving things down. So you're moving in opposite directions when you're using TLC versus column chromatography. In TLC, you're going to use a plastic plate coated with a thin layer of Silicagel. Again, the Silicagel is going to be your adsorbent or your stationary phase. That's going to absorb the compounds, and the solvent is going to travel up through the adsorbent, and based on the balance between the affinity of your components of your mixture for the stationary phase versus the mobile phase, you're going to get separation. And the same principle applies again with the column, except you're going to be moving down. The LUN travels down the column, and then you collect what comes out the bottom. And of course, you're going to be using a tube instead of a little tiny plate. And you're going to be using, in your column, you're going to be using alumina. So adsorbents, or stationary phases, are typically more polar than the LUNs. So the more polar a compound from the mixture is, the more strongly it adheres to the adsorbent and the slower it moves. If you want to move polar compounds down quickly, you need to go to a more polar eluting solvent. Okay, so the more polar the eluent is, the less strongly the compound will adhere to the polar adsorbent, and the faster it'll move, and vice versa. So before you do your column, where you actually separate and isolate ferrocene and acetylferrocene, you have to keep several things in mind. First of all, don't ever let your column go dry. Don't allow any part of your column to go dry. That means the level of the solvent drops below your sand layer. If that occurs, the equilibrium between the mobile and stationary phases is going to be destroyed. And then if you try to add fresh solvent again, it's going to take time to reestablish equilibrium, and by that time you may have lost some resolution, or your separating power. Really read very carefully the section in your lab manual, preparation of the chromatography column. It's got some very important instructions. You want to keep your column as vertical as possible. You, again, don't want to let any part of it go dry. And the way that you load your reaction mixture onto your column, and the way you get it adhered onto the column through the sand layer is very, very important, and will help you get really good resolution. And we chose this experiment because you can actually see the compounds eluting because they're colored. They're actually two different colors, the starting material and product. Typically, we separate compounds that you can't see, and so we collect things in a series of vials or fractions, and then we typically analyze each one to see where our products are. By the way, think about the purpose of the sand layer in your column. What's the main purpose of that? Okay, so here is an example of a reaction mixture of ferrocene and acetylated ferrocene. This is a different kind of column. This is not exactly the same column or same solvent system that you'll be using, but just to show this reaction has been done with different reagents, and it can be done, the separation can be done in a variety of ways. But you can see the first eluting material is going to be ferrocene, because ferrocene is less polar than acetylferrocene. So the ferrocene is going to be the bright yellow band that comes out first. From left to right, you can see the ferrocene coming down the column. And then you can, once you get the ferrocene off, again, it's going to absorb it's going to absorb more weakly than acetylferrocene, because acetylferrocene is more polar. You can switch over to a little bit more polar solvent and wash off your acetylferrocene, which is going to be darker in color. And yeah, in these solvents, and you're going to be using different solvents, you can see ferrocene is separated from the acetylferrocene, and ferrocene and hexane is yellow, and in the TBME solvent, acetylferrocene is reddish. So TBMB is more polar than hexane, and again in the experiment, in the example shown, hexane is nonpolar, and you're able to elute the ferrocene off the column first because it adheres less tightly to the stationary phase, and then you have to switch to a more polar solvent to elute the acetylferrocene because it adheres more strongly to the stationary phase. Okay, next you're going to run a TLC plate, and one of the main reasons for running a TLC plate is to get a retention factor, and the retention factor is just a measure of how far up your components of your reaction mixture move. And this is actually a reproducible measurement of physical property. As long as your stationary and mobile phases and temperature are constant, the RF of individual compounds are reproducible. And again, the same principle applies. If you increase the polarity of your eluting solvent, you're going to move your component more quickly up the plate. Now, coincidentally, two different compounds can sometimes have the same RF in a given eluent, but to get better resolution, you try different solvents. So here's an example on the far left of a really good separation, and in the middle there, not so good, and just over to the right there, also not such a good separation, and those three on the right there. So you'd want to try some other solvent systems in each of those. When you have all three spots moved to the top, as you see second from the right, either your stationary phase is not polar enough, or your solvent, more typically your solvent is too polar. And just to the left of that, second from left there, the solvent is too nonpolar. It's not moving your components far enough. On the far right, you have it. You have all three components moving, but there's really not such good separation. You may want to try a completely different solvent system in order to separate those. So your lab is going to involve a reaction, separation, and thin layer chromatography. Good luck.